Welcome to everyone who's here in person and online. As Fatima said, my name is Michael Kehoe, and this session is on eBPF, the next power tool of SREs. I have been given 30 minutes to try and talk about this really cool new framework in the Linux kernel. And I'm going to try and cover as much detail without getting bogged into Linux kernel internals, so bear with me if I'm too high level or too low level. Quickly, an agenda for today, I'll do an introduction and then go through the history of BPF. We're going to quickly show you how to get started with eBPF, how you can go and start writing your own programs. And then we're going to look through the sort of three main categories of capabilities that eBPF has. Firstly, around observability and tracing. Secondly, around networking. And then thirdly, around security. We'll then conclude talking about where the future is of eBPF and how, as SREs, we're likely to use it in the future with some cautionary words. All right, so if you didn't catch my talk yesterday, I'm Michael Kehoe. I work at Confluent as a senior staff security engineer. Previously, I was at LinkedIn. As Fatima said, I did an internship at NASA. I've worked on a bunch of different things over my time as an SRE. And if you want to contact with me, or connect with me rather, here are my socials. Quick plug, I just released this new book, Cloud Native Infrastructure with Azure, if you're starting to get started with Azure. And also previously wrote a book with a couple of peers from the SRE world on reducing mean time to detect for high severity incidents. All right, an introduction to eBPF. So put your hand up and keep it up, please, if you have used BPF before. All right, maybe a dozen. All right, so keep your hands up, please. Raise your hand if you've used TCP dump before. All right, way more hands. So whether you know it or not, those people who raise their hands for using TCP dump have actually used BPF before. You can please lower your hands. And I'll explain that in a second. So the last couple of years, the industry has sort of gotten a little hot about eBPF. But what you may not know is BPF has been around for a very long time. What's sort of now known as classic BPF has been around since the early 1990s. It was originally known as Linux packet filtering. And was introduced by Stephen McCain and Van Jacobson in BSD. It was first implemented in the Linux kernel 2.2, and it was called Linux socket filtering at that time. So BPF has been around for a really long time in Linux. As those people who raised their hands for using TCP dump might have connected with, it was originally used for network packet filtering, and then later on started to be adopted for some limited sec comp uses. Essentially, it works by creating a filter expression, so a TCP dump expression where you might want port 80 and destination host whatever. That gets then turned into bytecode and then gets run in an interpreter. And essentially, eBPF is an in-kernel virtual machine that uses registers and has a very limited set of instructions. If you sort of visualize this, this is what you get. So you have your TCP dump utility. You have a defined expression. A library called libpcap actually then goes and turns that, sort of parses that expression and then compiles it into BPF bytecode, which then gets pushed into the eBPF virtual machine, and those instructions are run. And as packets come through your network interfaces, those packets are passed in the virtual machine against that filtered expression that's compiled. And so what you end up with is a very highly efficient, high-performing network parsing or packet filter. So what is eBPF? So given the hype, I wanted to use some hype language. So from Brendan Gregg, who is a pioneer in this space. eBPF does to Linux what JavaScript does to HTML. Gaurav Gupta from SAP Labs says that eBPF is Linux's new superpower. Cilium, who write both open source and commercial software in this space, say that BPF is a highly flexible and efficient virtual machine construct in the Linux kernel that allows you to execute bytecode at various hook points, which we'll come back to, in a safe manner. It can be used in a number of different Linux kernel subsystems, most predominantly networking, tracing, and security. There are some others, but we'll skip them for today. So eBPF stands for Extended Berkeley Packet Filter. As I said, user-defined sandbox bytecode executed by the kernel. eBPF has a slightly more evolved virtual machine than classic BPF, and this runs in the kernel space. Most importantly, there are multiple verification layers to ensure kernel safety. And this is basically because you're running kernel module-like code in kernel space, but without having to go and write a kernel module, load that module into the kernel, et cetera. So the verification layers ensure that you can basically go and run anything safely without worrying about panicking your kernel. Interactions between kernel space and user space are typically done through what's called eBPF maps. This is a data structure. We'll go through them shortly. There's also a blocking trace pipe, which you can use for debugging, which you shouldn't in production. And somewhat importantly, eBPF doesn't allow loops. However, bounded loops were introduced in kernel 5.3. So you can run loops up to, I think, 1 million instructions within a program. So again, what does this visualize out to? So I've got a BPF program that I write. It goes and gets compiled into bytecode using either the LLVM or Clang. We then load that program into the kernel using the BPF syscall. And then within that BPF virtual machine, we take that bytecode, we go and verify it. We have a just-in-time debugger to make sure that we're ready to run it. It then gets run in the kernel, and it hooks against different kernel functions, which we'll talk about shortly. As I said, classic BPF was basically used for just parsing network packets. eBPF allows us to hook on to multiple different things in the kernel and run these programs. On the other side, we have our user space program, which again uses the BPF system call to access BPF maps to get data between the BPF program running in the kernel and the user space program, which we might be using to sort of display output or push that data into some other system. So I mentioned the BPF system call. This is one of 4 key constructs, which I'll very quickly go over. So the BPF system call has 36 different functions currently in master. Essentially, this allows you to create your maps, interact with your maps, and most importantly, load your BPF program, which is probably the most common use case. There is a bunch of other functions that I won't go into here. But essentially, this acts as the interface between user space and kernel space. We have 31 different program types. So as I mentioned, eBPF can be used for multiple different applications. And how this sort of works is by defining a program type. And so the program type sort of defines basically what is the program allowed to access in terms of kernel resources, but also these helper functions, which sort of provide macros for us interacting with the kernel. So we have currently in master 31 different program types. Over half of these are actually used for network applications. And there are some subtleties where some are very similar, but slight differences. These program types also help set the context, or basically the arguments that are pushed to the BPF program. So if you're running a tracing utility, your BPF program gets a different set of arguments to go and run the program against versus a, say, a network application where you're going to be given a socket buffer. eBPF maps. So again, these are generic data structures. It allows sharing of data between kernel and user space. As you can see, there are 30 different map types here. Basically, this allows for us to store different types of data. So you can put programs in there. You can put sockets in there. There's a lot of different data types that can be stored in these maps, and they can also be optimized for number of CPUs. So you sort of pin something to a CPU. I also mentioned helpers. So these are basically specific functions that you can run within your BPF program. There's 190 different helpers that are currently available. This continually grows. And they provide various different pieces of functionality. So the one up here, BPF trace print K, basically print something out through the trace pipe that your user space application can then go and print out, which I'll show you shortly. But there's other functionality like manipulating the data in those maps, different debugging functions, and then loading data from packets. As I said, there's 190. If you are using these helpers, make sure you check your kernel version for compatibility. We'll talk about kernel compatibility a little bit more. And also a pro tip, the man pages are sometimes out of date on your system. All right, so how do we get started with eBPF? So I've sort of condensed it into 4 easy steps. So first of all is run the most recent kernel possible. There are new eBPF functionalities being added to each kernel release. If you go and use a 3 series kernel or a 4 series kernel, you're probably going to give yourself some pain. So try and run something that is as recent as possible. There are a bunch of eBPF kernel configuration options, which I'm going to put on the next slide for reference in case you want to go and look at these slides in the future. All these kernel configuration options should be set to yes to enable them. If you have some of these disabled, you won't be able to run some different program types. For the purposes of getting started, there is a really awesome package called BCC Tools. I've linked the GitHub there. This sort of allows you to sort of go and install the package and start writing programs really quickly. So how do we do that? So these are the different kernel configurations and options. So it's as easy as running yum install BCC or on Debian or Ubuntu, apt-get install BPF CC tools. This will install everything that you need onto your machine to go and get started. And so what we'll then do is we'll go and write our Hello World program. So this is our first eBPF program. So I've tried to separate this into 2 things, the kernel space application and the user space application. So first of all, we go and import our BCCC library. And then we've got our kernel space program. So you can define this in a separate file. I've just put it in the text in the same Python file. But basically, I write a function that says kprobe sysclone. So basically, this says I want to trigger this function against a kernel probe, which I'll talk about shortly, when we hit the system call for clone. Within this program, all I want to do here is print out to my trace pipe, hello world. And then I also need to return a value. That's just semantics. Depending on the program type, you will have to return different values depending on what you're doing. In my user space application, I basically call BPF, and I say load this program, prog, which I've defined above, and then I want it to basically just trace print anything that's sent to the trace pipe. So what does this look like? So I ran this on my laptop literally last night. I run my eBPF demo.py, and basically every time sysclone is called on my laptop, I get this output. Nothing super exciting, but this is sort of the foundations of which we'll build off. So let's talk about capabilities now that we're done with the theory. So the first capability is observability. eBPF provides a number of different ways where we can get really high-performing, high-fidelity data out of our kernel to know how our systems are operating. So the most common type of observability program is going to be a kprobe or kret probe, if you want to get trigger when the kernel probe returns, or uret probes. So basically, it captures the entering or exit of a kprobe or a uprobe. So this is exceptionally useful for capturing information around disk operations, network connections, or even execution of programs. So if someone is trying to run something on your system, you can very easily go and capture that data and get enough metadata to go and log that somewhere useful. We also have these things called USDTs, which I believe is sort of like dtrace probes from Sun systems. So this basically allows us to capture user statically defined trace points in a program. Node, MySQL, Postgres all have these USDTs already in their software. So you can actually go and look up these different hook points in those 3 applications and then go and run a BPF program against those hooks. Theoretically, you could go and run or go and add USDTs to your own applications and then run BPF programs on top of that. And you definitely can imagine where this would be really useful in debugging or profiling your application. We also have trace points. This allows you to instrument predefined trace points in the kernel code. In some places, this can be much higher performance than kprobes. I would argue they're sort of less convenient to go and implement, but it may suit your use case. If you want to also run programs against the perf events in the Linux system, you can also do that. Very quickly, I'll go through a sort of more general use case of an observability tool. This is taken from the BCC library, so you can go and, if you go and install the BCC tools, you can go and run this for yourself. So this is disksnoop.py. Basically, on this slide, we have 2 functions. One that runs called trace start, which basically gets the time from the kernel and then puts it into a BPF map. And then we have trace completion, where we go and look up the corresponding request in the map, get the time from the kernel, and then we go and print out some debug information to our trace pipe. As I mentioned earlier, you probably don't want to run this sort of thing in production, just because the trace pipe is blocking. And then on the user space side of my application, I basically attach these 2 kprobes. So I'm attaching them to block.io kprobes, and I reference the start trace and start completion functions that I want to run when we hit these kprobes. And then within my user space application, basically, I just keep pulling information from the trace pipe, and then I go and try and put some extra metadata together, and then print it out. And it looks something like this. So this basically logs all the block.io requests that have gone through the system. You can see if they were read or write applications, how many bytes, and then how long those operations took. Second capability is networking. As I said, over half of the different program types for eBPF are actually networking based. Given that this is a 30-minute presentation, I can't literally cover any of this in detail, unfortunately. But I do want to give you some information about how eBPF can be used in the networking sense. So the first one is load balancing. Within eBPF, we have a program type called XDP, which stands for Express Data Path. This allows us to bypass large parts of the TCP IP stack and do really, really, really fast network load balancing or port forwarding. And we can scale up into the millions of packets per second. So you may have heard of Facebook's load balancer Katran, which is open source on GitHub. Cloudflare also very openly talk about their eBPF load balancers. And this is actually, you can find a number of tutorials on how to write your own XDP-based load balancer, and it's actually reasonably straightforward. The second use case is network filtering or DDoS protection. So as I mentioned, BPF sort of got its roots from network packet filtering. And so in eBPF, this still holds true. We can write very highly efficient network firewalls or network packet filters, and again, scale it up into the millions of packets per second. Third use case is traffic control. So if you've ever used TC on your Linux system, eBPF supports attaching programs to TC events. This is sort of obsolete now, but it's still, there's still functionality in eBPF for it. Next one is control of sockets. So there is a large amount of socket manipulation you can do with eBPF. So everything from like changing socket options after the socket's been created to sort of splicing sockets. It gets really complicated really quickly, and I'm not going to go into any further detail, but there is a lot of really powerful functionality there to do really high performance, like hyperscale networking. The final thing I'll mention is flow dissection. So if you need to do flow dissection at scale, capture metadata about the traffic that's flowing over your network, you can go and write your own flow dissection program instead of using the inbuilt one in the Linux kernel. Some quick resources to find out more about eBPF networking. So as I mentioned, Katran. If you're using Kubernetes, you may have heard of Cilium or Hubble. This is an add-on to Kubernetes that allows you to do network-based network load balancing and firewalling, which also does replace IP tables. And if any of you have run Kubernetes in a high-performance environment, you may have sort of faced some of the performance challenges with IP tables in Kubernetes. Calico, which is a Kubernetes network plugin. Cloudflare Edge Infra, like basically all of Cloudflare's POPs, they're all running eBPF programs to do all of the load balancing, firewalling, WAF applications, etc. You can find more information on the BCC repository. There are some networking, very basic networking examples, which are a good place to start with. If you want to hear about the really complicated stuff, the Cloudflare blog has some really amazing detail in how to like go really in depth if you're interested. The third use case is security. So there's 4 primary security program types. The first one is for C group devices. So this allows you to run a program that sort of controls or monitors the usage of a host device within a C group. So you can basically write some custom logic that sort of allows the child container to go and have access or be denied access to a host's device. Similar thing with syscontrols. And of course, we have a special program type for doing network packet filtering for C groups. The final one is Linux security modules. And this is probably one of the more interesting ones, and it's also one of the newer program types. So this allows us to instrument a Linux security module hook as a BPF program. So sort of similar to kprobes, the Linux kernel also has these different security hooks as well. And things like AppArmor or SELinux use these today. But what we can go and do here is we can sort of go and write our own version of AppArmor or SELinux if we want, and utilize these these LSM hooks to go and run our own BPF applications on top of that, and provide mandatory access control policies through BPF programs, but also go and audit security events in real time. So I thought it'd be fun to try and write a very, very basic example. So here I have an LSM probe function. And the first argument in my function here is file open. And this is one of the LSM hooks. So if I go and try and open a file via any of the different syscalls, my probe is going to, this program is going to fire. So first thing, I'm just going to print out, hey, LSM hook, file open. I then go and get the current process ID that is triggering this program. And then what I'm doing here, and this is sort of dumb but works for the purpose of an example, if the process ID is not process1 or init, I'm going to deny access to the open function. So I'm going to return eperm. Otherwise, I sort of allow it. I put that into my trace pipe, and I return 0, which means that basically the init process can go and run open functions or open syscalls, but nothing else can. On the user space, it's pretty much straightforward. I load my program. I basically attach the file open LSM, and I say this is a BPF program type of LSM, and then I'm just going to print the metadata associated with this program running. So you'll get, with the trace fields helper, you get information about the user, the process, and some extra metadata that you could then go and push into a logging system. All right, I've got 3 minutes left. So the future of eBPF and SRE. So again, I've broken it down into our 3 capabilities. So for observability, we can troubleshoot low-level issues without worrying about performance, to the point where we never have to use strace again. If you're running anything in production and you decide to run strace, you can definitely be in for a very difficult time. strace can add hundreds of times of overhead into your system calls and can be very dangerous. With running kprobes or trace points, we don't have to worry about that again in the eBPF world. There is a negligible overhead of maybe 1%, depending on which syscall and the frequency. But eBPF allows you to do this low-level tracing and performance analysis without having to worry about the system. And this really opens us up to new possibilities to go and optimize our own user code that we're writing and putting on our production systems, but also go and sort of locate kernel bugs as well. For networking, there is definitely a lot of stuff out there already in the Kubernetes and Cilium world that is using eBPF. Cilium is pretty good at adding new functionality for their product every time there is a new BPF program type that comes out related to networking. So some of the newer program types around tunneling, building lightweight tunnels is already in there. This also allows us in the networking space to do hyperscaling for everyone. So you don't have to be a hyperscaled company to go and do really high performance firewalls, load balancing, or WAFs. A much smaller company can go and do that themselves now. And then finally, security. So there is deep integration with the Linux security modules to go and get real-time, rich security data, which allows us to go and ensure that our systems are safe and secure. And we also, of course, have the C-group protections for device access controls and network traffic. I do really see, over the next couple of years, a lot of people latching onto LSM functionality to build products to ensure that systems are safe and the programs that we run on our systems aren't being compromised. Couple of words of caution before I go. So I've spoken a lot about the awesome performance of eBPF. Caution, you can still harm your system if you're not careful. So make sure you're well aware of your performance boundaries and limitations. If you can't afford a 2% regression of your system's performance, you might run into some issues. So always test very diligently. Second thing is be wary of OS and kernel capability. So as I said, there are new functionalities being added to each kernel version. Make sure that you test this and don't assume anything. A word of caution as well, CentOS and Red Hat often backport a lot of this functionality to their older kernels. So you'll see functionality from like 4 series kernels and 3 series Red Hat kernels. You will need to think about your deployment strategies. And so over probably the last 2-3 years, Facebook introduced this thing called CORE, which stands for Compile Once, Run Everywhere, which makes it easy to go and run your BPF programs. But this is something you will have to think about, especially if you're going to run a large number of programs. For context, in a presentation in, I think, 2019, Facebook said they were running 40 different BPF programs on all of their production systems at any given time. You can also run programs via systemd. And of course, last but not least, while eBPF is kernel safe, you still should thoroughly test your code before you run it into production. I will leave in my slides some references on where to get started. I actually did a BPF workshop a couple of years ago at a different conference. All that material's still up there and relevant. And here are some other great resources to go and get started with eBPF. Thank you very much for your time. I'd love to now entertain any questions that you may have.